My pleasure. All right.
So for the process 2 to 3, it's isothermal heat addition. Isothermal means T2 is equal to T3, constant temperature. Process 2 to 3, heat addition, I'm adding heat. Process 1 to 2, isentropic compression, that's what the compressor does. I put in work in. Process 3, going to 4, again, is isentropic. Work out. Or isentropic expansion. Again, is S3 is equal to S4. That's the definition of isentropic. Going back, process 4, 1, once again, we have isothermal heat rejection. Again, T4 is equal to T1. So these are the 4 processes identifying Carnot cycle. So if we want to change this from other Carnot cycle to any other cycle, these processes are going to change. Now, for every cycle, we should have TS and PV diagram. In this case, we don't need a PV diagram. Let's look at the TS diagram. That's temperature versus entropy. Now we look at the first one. It says 1 to 2 isentropic. That means if I have point 1 here, I have to go straight up. Perpendicular, this is 1 to 2. S-axis, make S1 equal to S2. That's my point 2. Now process 2 to 3 is isothermal. That means I go straight, parallel to this axis, or perpendicular to t-axis to get 0.3. That's where I have T2 is equal to T3. Now here I have expansion. I'm going down. So this is 3 coming to 0.4, and S3 is equal to S4. Finally, 0.4 is connected to 0.1 at a constant temperature. So I started at 0.1, went to 0.2, 3, and 4, and back to 1. Now, please take a look at this. Why this cycle doesn't work? Why this is only theory? Very obvious. Process 1 to 2 and 3 to 4 is no problem. However, how can we add heat but keep the temperature constant? Can you do that? Can you boil the water at a constant temperature? That's the easiest example. Process 4 to 1. How could we cool down something at a constant temperature? You get a Coke, Pepsi, your drink. It's warm. You put it in the refrigerator to get cold. Can you tell me the temperature of the Coke that you're picking up from the refrigerator is the same as the temperature before you put it in? That's impossible. So that's why this concept is very theoretical, but it was the start. Once the cardinals start this, we realize where the problem was and start thinking about modifying to generate power. Now, your TS diagram always correspond your equipment diagram. You don't have to memorize any of these. You develop this based on what you have here and based on your processes. Now, one of the things that I tell you to practice for isentropic process, always put a dash mark, because later on you'll see the importance of it. Now, you can write this statement. All compression and expansion happen. Whoops. This is an important statement you need to remember for the rest of the semester. All the compression, all the expansion, always, 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 without exception, happen isentropic, constant entropy. Chapter 9, 10, 11, you'll see that. So at least you know two of the processes remain the same regardless of what kind of a cycle we have. So that's something you need to make a note and remember. So as you can see, that's why we have problem making this actually work. Now let's go around the cycle and find the quantities of energy that we put in and we get out. First one, the work in. The work in or work of a compressor is H2 minus H1. Delta H costs the equipment, H2 minus H1. Now the Qing heat we add into it. Delta H costs the equipment, H3 minus H2. The work we get out of it, work out, is H3 minus H4. Now everybody say, how come it's not H4 minus H2? Because the subscript doesn't mean anything. These are arbitrary. This is what we assign. In thermodynamics, there is absolutely no negative numbers. We don't have negative energy. So all numbers always have to be positive. So if I put H4 that has lower H value minus H3, then I would get a negative number. That's not how it works. So we always deduct the smaller number from the bigger number. We don't care about the subscript. As you can see here, H2 minus H1 makes sense because this is a low temperature, higher temperature, low temperature, higher temperature. Enthalpy depends on the temperature. H3 minus H2, that's the amount of heat we put in. Look at that. If T2 and T3 are the same, what happened here? This becomes zero, right? That's why it doesn't make sense. Now, here we have very high temperature, high pressure, therefore very high enthalpy. Lower temperature, lower pressure, because we expand, we lost most of our pressure and temperature. Therefore, we have a lower enthalpy. So we deduct this point from that, H3 minus H4. Finally, Q out would be H4 minus H1. H4 minus H1. Once again, if these two temperatures are the same, that means these two H are the same. So this becomes zero. If Q out is zero, Q in zero, what happened? Work in is equal to work out. Does that make sense? No. We're in a business of generating energy, not just wasting our time, plugging something in and getting the same thing out. That means you create energy out of nothing. And as we know, it's against the first law of thermodynamics. So this process or Carnot cycle is very theoretical. It doesn't work. You don't have to worry. We're not going to have any examples or deal with it or nothing at all. But it's good to know the basics and the concept. Any questions? Now, let me define a few other things that you will need to know. Let's use the first law of thermodynamics. I have work in plus Q in one side. I'm putting into the cycle. This has to be equal to work out plus Q out, right? Summation of all energy going in is equal to summation of all energy going out. If I rearrange this equation, this becomes work out minus work in is equal to Q in minus Q out. Once again, work out should be bigger than work in. Q in should be bigger than Q out. That's why we deduct the lower number from the higher number. This is very important. This is what we call network, W net. So the network of any system is equal to either work out minus work in or Q in minus Q out. That is called network, most important. Now, I want you to remember something. In thermodynamics, we have just a few equations. Everything else, we develop it ourselves. For instance, this is the only equation. All of these that you see are not equations. This is, we made it ourselves. Based on a definition of the value of energy is basically a delta H, cost of equipment. If I have 10 numbers in the cycle, the work in and work out could be totally different. So we create those, we develop those as we go in. See how many work we put in, how many work we put out, how many heat we put in, how many heat we get out. You'll see that in the future. So these are not considered as an equation because it can be changed. This is the only equation so far. You will see just a few. The rest of them is the one that we develop as we go in and as we see different cycles. So just remember that this is what we're after, the network. We want to see what is the network coming out of this cycle. That is the power that we are generating. That's that. Don't forget that. The network is what we are after. That's the outcome of putting this cycle together. Now, how do we measure the quality of cycle? We already told you about quantity. Now we want to talk about quality. We measure the quality by the thermal efficiency. That's eta TH. That represents efficiency, and that's thermal. The thermal efficiency is described as desired output divided by heat in. Looking at this equation, what is our desired output? Network. So the network divided by Q in will give us the thermal efficiency. That's the second equation that we need to know. These two equations work in chapter 9, 10, and so on and so forth. Regardless of the cycle, this will never change. Always stay the same. I'm looking at this. Can I rearrange this? If I look at up here, I see the network is Q in minus Q out. So if we replace the network with Q in and Q out, I will get 1 minus Q out over Q in. These two are the same, so it's not, all I did, I replaced the network with Q in minus Q out. Once I do that, the first part becomes 1, the second part becomes Q out over Q in. That's how we define the quality of the power that we generate. The efficiency, the thermal efficiency. Don't forget that. Thermal efficiency of the cycle. Any questions? Okay. No. Now, let's forget about Carnot cycle and talk about semi-ideal cycle, which is Otto cycle. Did you guys write all this statement? Because I want to erase that.
Yes.
Yeah. Good, thank you. What about this relationship?
Yep, I'm good.
Okay? All right. As you notice, I didn't change the equipment diagram. I kept it the way it was. However, this time, the processes gonna change. Let's see what we did a change on this process. Now, process 1 to 2, we already know. Nothing's going to change. Isentropic compression. S1 is equal to S2. Now, this time we change process 2 to 3, and we call that isochoric heat addition. That means V2 is equal to V3, constant volume. Process 3 to 4, once again, is not going to change. Isentropic expansion. S3 is equal to S4. Finally, process 4 to 1, again, isochoric heat rejection. Meaning V3 is equal to V4. Now we have 4 brand new processes. So now, this is a cycle that we need to have 2 diagrams, PV and TS diagram. Now, here we go. This is our TS diagram. This is pressure versus volume. Now I'm showing you how easy it is to draw these diagrams. First of all, for your information, all these diagrams in your textbook. And when you're taking the exam, is open textbook. So you can always look it up. Nothing to memorize. But if I know how to do it, it's going to be very helpful. Let's see if we can do this based on information we have. 1 to 2 isentropic. That means we are here. So that's 1 going to 2. And I dash that. So I have isentropic process. Process 2 to 3 is a little different. This time, process 2 to 3 is at constant volume. I have process 2 going to 3 at constant volume. Process 3 to 4 again, it's expansion. So that's 3 coming to 4 isentropic. And process 4 to 1 is isochoric. Okay, I have 2 diagrams, all this. What I'm going to do?
Professor?
I'm simple. To connect 2 and 3, we look at 2 and 3 here. This is a straight line. This becomes a curve. And the curve is exponentially going up because we are heating. It has to go up. So here, 3 to 4 is basically straight line. So we have to go down exponentially to get to 0.4. So this is now expansion, which is isentropic. that represent this isentropy here on the PV diagram. Process 4 to 1, we already know. Process 3 to 4, again, I'm sorry, process 4 to 1 is a heat rejection. So I have a straight line here. This is process 4 to 1. Here, process 1 to 2 is isentropic, straight line. Going up, that means, again, a curve making point 1 connecting it to point 2. And since it's isentropic, I dash it so I don't forget. I have a TS diagram, I have a PV diagram without looking at the textbook and copy it down.
Professor, I had a question.
Yes,
In the fourth process, did you write V3 equals V1 or what is that? V3 equals V4?
3 to 4.
In the isochloric heat addition, rejection.
This is 4 to 1 is
Yes.
quick heat rejection.
Mm-hmm. And then the last nomenclature at the end, the V.
V3 is equal to V4.
Okay. Shouldn't it be 4 to 1 or no?
I'm sorry, this is.
Thank you. Yeah, no problem. Thank you so much.
Mistake, V4 is equal to V1. My bad. Thank you for catching that. Well, this is great. I'm happy you caught that because you need to pay attention. You can catch your mistakes very quickly. And you saw that I made an error here and you caught it right away. Thank you. So, as you notice how easy it was to do these diagrams without getting any help from anywhere. Now, I still have the same work in this case. This is my work in. The opposite side is work out. This is my Q in. This one is my Q out. Same thing here. This is Q in. Opposite of that is Q out. This is the work I put in, and this is the work I get out. So both my TS and PV diagram represent my equivalent diagram as well as representing my processes. Simple. Now we look at how we're going to determine the quantities of various energies around the cycle. Now, first quantity will be work in. Work in is an isentropic process. So that means H2 minus H1. Now, Qing, what's the process for Qing? It's isochoric. What did we say about isochoric? The exception of that, this would be U3 minus U2. Delta U, internal energy, not mental. The workout is not isochoric. So that would be H3 minus H4. And then finally the Q out would be U4 minus U1. These are the various, that's why I said none of these are equations. We develop these based on what we have in our cycle. But at the end of the day, the difference between Q in minus Q out will give you the network. That never changes. Or work out minus work in will give you the net work. Doesn't matter which way you want to go. Finally, thermal efficiency is the net work divided by Q in. These two equations remain the same, regardless of how you calculate all these energy values. This will never change, this will never. Now, in case of an auto cycle, as we notice, we need to draw both TS and PV diagrams in order to solve a problem. If you don't have these two diagrams, you're gonna be in trouble. Because through these diagrams, you develop this relationship, and you know you have to go to the table, finding H1, H2, U2, U3, H4, H3, U1, U4, in order to find all these values. If you don't know that, if you don't see that, you can solve the problem. So if the problem is given out of cycle, the first thing you need to do is draw these two diagrams. Then you go and solve the problem. Any questions? I want to look at the okay. Now, you remember I said there are two ways to solve a problem. Everything we said here is the thermodynamic way. You have a temperature, you go to the table, you find the values of H or U, you find different quantity of energy, and you find the network, and you find the efficiency. The way we can do the heat transfer is only one condition. If you remember at the beginning of the class, we made a huge assumption. And our assumption was that basically we consider that air or air standard is ideal gas. Right? Now, the second assumption that I can make, if I say that Cp and Cv are constant. As you know, that we talked about it last time, both Cp and Cv are a function of the temperature. Temperature changes, these values changes. But if I consider them as a constant, then it will make my life much easier. For instance, if Cp and Cv are constant, the work in becomes Cp times T2 minus T1. The work out becomes Cp times T3 minus T4. My Q in becomes Cv, because it's constant volume, times T3 minus T2. And my Q out, again, would be Cv times T4 minus T1. As you can see, it's much quicker, much faster. I don't have to go through the table, waste my time. Sometimes you have to interpolate between the numbers. All of that, all of a sudden, instead of spending half an hour to solve a problem, I solve the problem in 10 minutes. The only difference is this is based on a huge assumption. Once you make that huge assumptions, your answer is not accurate. So we seldom use this concept in a real life. We never ever consider CP and CV a constant. We always, in a real life, do it the hard way, do it thermodynamically, not heat transfer. Now, there are a whole bunch of stuff associated with this that I will go over it with you in a few seconds. But I just want to run this by you, see how these things work. Now, let's see how we solve the problem, because all of that is nothing if you don't know how to go around the cycle and solve the problem. I'm going to get rid of the processes. I'll show you all of this. Now, this is when being organized will help you a lot. You need to start from one, state, go through the cycle, and find the rest of the values. Okay? So in order to do that, let's say, for instance, what are the given values? Oh, before we do that, there is another relationship related to auto cycle. Number one is compression ratio. This is defined by maximum volume divided by minimum volume. What is our maximum volume in this case? Look at the PV diagram. Our maximum volume is V1. Our minimum volume is V2. So the compression ratio, we call it R. In your textbook, it's called just R, but I will say R of C. Compression ratio is going to be V1 over V2. That's very important, the compression ratio. There's another thing associated with auto cycle. Once you have that, the other one is relative volume at the given point. And we show that as R of V. That is the relative volume at the given point. How many points we have? 4 points. So R of V1, oh, I'm sorry. V of R1, V of R2, V of R3, and V of R4. That's a relative volume. Oh, made a mistake. This is R of V. Compression ratio is a ratio of volume, so R of V, not R of C. So This is what we have relative volume. There is a relationship between the compression ratio and relative volume. For instance, V1 over V2 is equal to VR1 over VR2. Now, please, don't make a mistake that since this is true, so V1 is equal to VR1, V2 is equal to VR2. Absolutely not. Their ratio are the same. Their values are not. So V1 is not equal to VR1. V2 is not the same as VR2. But their ratio are the same. Similarly, V3 over V4 is going to be same as VR3 over VR4. Look at this. What is V3 over V4? The V3 over V4. It's a reverse of a V1 over V2, right? We said the compression ratio is V1 over V2. So if I go the other way, V3 over V4, since they have the same volume, that would be, this becomes 1 over R of V. What is this one? This is R of V. That's a compression ratio is V1 over V2. Reverse of that is equal to V3 over VR4. You need to know these because that's how we're going to solve problem either from the heat transfer or going to the textbook, what we call the tables. Any questions so far? All right. Now I'm going to erase this. Now, to solve a problem, let's say we have an example. Of course, I'll do the actual example. I just want to run through this for you. For example, in an example, they always give you R of V. Let's say it's 8. That is equal to V1 over V2. We know that. Then they say the temperature at point 1 is 27 degrees Celsius. That's plus 273, that'll make it 300 degrees Kelvin. Then they say the temperature at point 3 is equal to 1800 degrees Kelvin. These are what we call given information. They say find network and find the thermal efficiency of the cycle. This is how I solve a problem, get myself organized. What's a network? I write the equation in front of it. So I know I have to find Q in and Q out. What is this one? This is the network divided by Q in. This will help me to understand the values that I need to find. So I don't go out of my way, find work in and work out. Why? You just do the things that you need to do. Your job is to find the easy way out, not doing it the hard way. So the way I do it, I go at the state one. What do I have at the state one? I have P1, oh, by the way, one thing I forgot. And P1 is 95, let's make it 100 kilopascal. That's information is given. At state one, I have T1 equal to 300 degrees Kelvin. Now, I go to table A17. Again, this is a time you need to have your textbook with you all the time. Because that's how you can learn the values that you need to find from the table. At the end of your textbook, there's an error table A17 and also A17E. Table A17 is for assignment. A17E is for English. So what do I do here? I go to the table. What do I need to know? Q in and Q out is based on the U values. So I don't need the H value. So I will find the U1 and VR1 from the table. I'm done with the state one. Now I go to state two. I write V1 over V2 is equal to VR1 over VR2. This side is given, 8. What do we have this side? VR1, I just found it. What's unknown is VR2. So I find the value of VR2 based on the calculation. From VR2, I go back to table A17 again. This time, I can find the value of U2 and also find the temperature at point 2. Just please pay attention. I had the temperature, I found the U value and VR value. Now that I have VR value, I find the U value and the temperature. So you go always back and forth to the table. Any questions? Let me raise the TS diagram.
Professor,
Yes.
please, what did you write beside the T1 equals to 300 Kelvin in the givens?
This is an arrow.
Oh no, in the givens up there.
Oh, in the given.
Yeah.
That's the example.
Oh no, sorry. What did you write beside the T1 equals to
27 degrees Celsius plus 273, you convert it to degree Kelvin. The pressure is 100 kilopascal.
Okay, thank you. Thank you.
No problem. So I'm done with the state 2. Now I go at state 3. T3 is given to me to be 1800 degrees Kelvin. I repeat what I did at point 1. Once again, I go to table A17. This time, I will find U3 and VR3. I'm done. Go to state 4. Again, I'm going to do the actual example so you get the hang of it. Just want to walk you through it. Now, the state 4, I'm going to write VR3 over VR4 is the same as V3 over V4. And this is 1 over R of V. R of V was 8. This is 1 over 8. What's unknown? VR4. In thermodynamic, always, we have one equation, one unknown. This is not a math course. You're not going to have 2, 3 equations with 3 unknowns or any one of those. Okay, so you don't have to worry about it. If you end up with 2 unknowns, you've done something wrong. So from there, I will find the value of VR4. Whatever that value is, I go back to table A17, and I find U4. If the problem asks, I will find T4. If not, I don't even bother with it. You don't want to do extra work because you don't get extra credit. So I went around the cycle. I find U1, U2, U3, and U4. So I come here. What is my Q in? My Q in is equal to U3 minus U2 minus, what is the Q out? U4 minus U1. That's how I found the network. I have the Q in, I have the network, I divide it, and I get the thermal efficiency. The thermal efficiency is always less than 1, and we show it as a percentage. 30%, 40%. You cannot go over 1. What happens if you have 125% efficiency? That means you generated electricity from nothing. Can you do that? No. First law of thermodynamics. You cannot create it, you cannot destroy it. If you get a negative efficiency, that means you destroy the whole energy. You cannot do that either. Watch out for those. Those are very, very important. Again, I'm going to do the actual problems with numbers, but I know you don't have your book with you, so I don't want to waste your time. But comes Wednesday, when I'm doing the actual problem, please, for your own sake, make sure that you bring your book with you.
Professor, a quick question. In step 4 at the very end, after VR4, use table A17 equals, what is the last part there?
Okay. Once I find the VR4, I go to the table, I find the U value and the temperature for that point. If the problem asks me to find the temperature, if the problem doesn't ask me, I'm not going to waste my time finding it. Why should I? That's why I just cross it up. But we found the value of U4.
Okay, thank you.
U1, U2, U3, U4. That's the only thing we need. Now, those were the only thing we found to help us out. Did that answer your question?
Yes, thank you very much.
No problem. Any other question? Okay. Now, let's see if you want to do the same problem to thermodynamic solution rather than basically, I'm sorry, heat transfer solution rather than thermodynamic. All right, let's do this. So we still have T1 and T3 and all of it. We need those. Now, there are some ideal gas equations you should know about this. That's from your earlier course. Ideal gas equations for isentropic processes. It says T2 over T1 is equal to V1 over V2 to the power of K minus 1. Now, the only time you can use these equations, again, when Cp and Cv are constant. That means in the problem, part of a given information, this has to be there. If it's not, you cannot use these equations. Okay, please read the problem carefully. If that's not the case, that means you have to do it the hard way, this way. If this is a case, your life becomes simple. From there, we already know the value of this is 8, K is 1.4, T1 is given. Very quickly, we find T2. State 1, we didn't do anything because we already have the value. At state 2, I use this equation to find T2, nothing else. Now, state 3, I already have the temperature. I don't have to do anything. So I go to state 4. T4 over T3 would be V3 over V4 to the power of K minus 1. This happens to be 1 over 8. T3 is given, K is 1.4. From there, I will quickly find T4 value. Now that I have all T values, let's say Q in is CV times T3 minus T2. And Q out is CV times T4 minus T1. And of course, the network, regardless of how I find this, stays the same. And the thermal efficiency stays the same. These two never change. So going through all these steps, back and forth with the table, and 2 or 3 times interpolation versus something can be done in 5 minutes. The only thing is, you need to make sure this exists. And these are all isentropic equations. 1 and 2, 1 and 2 isentropic, 3 and 4 isentropic. You cannot use it for 2 and 3 or 4 and 1 because they're not isentropic. So that's 2 ways of solving a problem. If Cp and Cv are constant, find the easy way out. Very quickly, 5 minutes, you're done. If Cp and Cv are not constant, then you have to go do it the hard way. Any questions?
Professor,
Sure.
what did you put in the exponential of V1 over V2? Is that K close to 1?
V1 equal to 1.
Oh no, the
Here, V3 over V4 is 1 over 8. V3 over V4 is a reverse of V1 over V2.
Oh, yo, sorry. I mean the exponential, what you wrote outside the bracket of the V3 over V4.
That's K1 minus K minus 1.
He might, okay.
K minus 1, K, this equation doesn't change. Subscripts are changing. This is K minus 1, this is K minus 1. Is that what you wanted to know?
Yes, thank you. Yeah.
I actually had a question that you kind of touched on the last question you answered. That 1/8, that is an exponent for the CV.
1/8 is the reverse of 8. R of V, V1 over V2 giving to be 8. What is V3 over V4? Look at your PV diagram. V1 over V2 is given to be 8. If you go to the opposite direction, V3 over V4, what would be that? It's a reverse, 1 over 8.
Thank you, Professor. That makes a lot of sense.
No problem. Again, I beg you not to chat in my class. Please stop doing that. You're distracting me and you're distracting everyone else. Don't chat with me, don't chat with anyone else. Show some respect. Okay. Any question on these so far? Okay. There is one equation in your textbook I want you to be aware of it. MAE336. If you look at your textbook, equation 9.8, in case of a CP and CV are constant, you can find the thermal efficiency very quickly. It's equal to 1 minus 1 over R of V to the power of K minus 1. Keep in mind, you have to have this condition in order to use this equation. As you can see, without going through this process, finding all these values, I can find this one right away. So that's another easy way out for thermal efficiency. Okay. Last part of the Otto cycle, there's a concept called mean effective pressure. We call it MEP. And by definition, mean effective pressure of the cycle is a network divided by maximum volume minus minimum volume. This has nothing to do whether CP or CV are constant. It doesn't matter. Once you find the network, you divide it by these two, then you find MEP. Now, how do we do that? In order to work on this, what do we have? We have V1 over V2 in our example is equal to 8. However, I don't have the value of V1, I don't have the value of V2. I went through this process or the other process, I found that network. So what do? I look at this value. I said P1, V1 is equal to R T1. P1 is given to me, T1 is given to me, R is universal gas constant. So I can very easily find the value of V1, let's say to be 0.98, just for the sake of it. Or 0.88, just putting a number. Now that I have V1, through this relationship, I can find V2. So V2 is equal to V1 over 8. And that will give me 0.11. Now I have V2, I have V1, I have network. What is my unknown? MEP. And MEP, let's say, becomes 400 kilopascal. Again, none of these numbers are correct. I'm just making this up. So this is the last part of basically auto cycle. With that, we already gone 5 minutes over. I apologize for that. Now, next time I will solve an actual problem. Please review this carefully. Bring your textbook, do actual problem. Any question you have, I'll be glad to answer it, because right after that, we go to the most important cycle, which is a diesel cycle. Thank you all. Have a good day, and I'll see you Wednesday.
Thank you, Professor.
My pleasure. And for those of you interested to talk to me on a office hour, please stay on.